So in this video, we will discuss the basic concentration problem assignment from the previous video. So in here, we're gonna solve the different problems about solving concentration. So let's start. Number one, the laboratory technician prepares a sodium nitrate solution by dissolving 12.8 grams of sodium nitrate with a molar mass of 85 grams per mole in enough distilled water to make 500 ml of solution. So in this video, I'm just going to be straightforward. If you want to if you want to have a detailed explanation, you can look at my previous video about concentration problems. So in this one, let's start by the given grams of sodium nitrate. So we have, okay, let's change color. So we have 12.98 grams of sodium nitrate with a molar mass of um, 85 grams, 1 mole. Okay, if you remember, molarity is equals to mole per liter. Now we got the mole of solute. Now we want the liter of the solution. It was given here the volume of the solution, which is 500 ml, but we must convert it to liters. So 1 mole is above, liter is below. But we were given ml, so let's convert it to liters. So 1000 ml is 1 liter. Okay, we can cancel that. And now we're left with 1 mole per liter. Then we can calculate that 12.98 times 1 over 85 times 1 over 500 times 1000. So that would be 0.305 molar. So that is the final answer. And next, so in a quality control laboratory, 5.60 grams of potassium bromide with a molar mass of 119 grams per mole is dissolved and diluted to a final volume of 200 ml. So this is just like the previous question, you know? Okay, so we have the grams of solute and we have the volume of the solution or the final volume. So let's start with the grams as usual. Okay, 5.60 grams of potassium. Oops, sorry. 5.60 grams of potassium bromide. Okay, we were given the molar mass of potassium bromide, which is 119 grams per mole. So 1 mole of KBr is 119 grams. If it is not given, you must check the periodic table. Next, now we get the mole, right? So we can cancel this. So we want a liter of solution. So we were given ml again. So let's convert that to liters. So 1000 ml is 1 liter. Okay, and cancel ml. Now we're left with moles per liter, which is molarity. 5.6 times 1 over 119 times 1 over 200 times 1000. And the final concentration would be 0.235 molar. Okay. Okay. Next. So number 3, you're asked to prepare 250 ml of 0.300 molar magnesium sulfate using magnesium sulfate heptahydrate. How many grams of the hydrate must be weighed out? Okay, so this is a similar concept from the previous video about concentration problem, right? So we are asked to prepare 0.300 molar magnesium sulfate. but we are starting not with magnesium sulfate, but with another reagent called magnesium sulfate heptahydrate, which when dissolved will eventually become magnesium sulfate. So this is just its hydrated form. Okay, this is pretty common in the lab because most reagents are hydrated. Okay, so to solve this, have we start. Okay, we start with the concentration. Okay, 0.300 mole of magnesium sulfate. Okay, that's the final concentration you want to solve. Mole per liter. This is molar. So times. Now we want the stoichiometric stoichiometric ratio from magnesium sulfate and magnesium sulfate heptahydrate. Now 1 mole of magnesium sulfate is also what? 1 mole of magnesium sulfate heptahydrate. Why is that? Okay, I have explained this, but you can see there's only one magnesium sulfate in one magnesium sulfate heptahydrate. If like this, for example, what if we are looking for the water? 1 mole of magnesium sulfate times 7H2O. How many mole of water? There's 7 mole of H2O. Okay, that's basically it. But this is just an example, okay? Because maybe some of you are confused in this one. Okay, so that's their ratio. It's 1 to 1. So this is basically one. I'm just showing you why how did we came up that from magnesium sulfate if it become magnesium sulfate heptahydrate. Okay. Now using the molar mass, we can calculate for the mass of the magnesium sulfate heptahydrate. Okay. We were given the molar mass of magnesium sulfate, but this is just magnesium sulfate, okay? This has times 7H2O, okay? So means it has 7H2O more than the um 720.37, okay? Plus 7H2O. So H we know is approximately 1. O approximately 16 since this is 2 or 2H. So this is 2. 2 plus 16 is just 18. So 7 times 18, that's the approximate amount of water. Okay. But this is close enough. I think it's 18.02 or something. Okay. But this is close. We can do this just for fast calculation. Okay. Now we can cancel the mole of magnesium sulfate, the mole of um, magnesium sulfate have to hydrate, but we still have liters. Okay, so let's calculate that. We almost forgot it. 250 ml. So this is the final volume. Let's use that. Okay, 250 ml. Since we want to cancel it by liters, let's convert that to liters. 1 liter. Okay, and then 10. So the final answer would be. So let's see. 0.300 120.37 7 times 18 times 250 over 1000 18.48 molar. Oh, sorry, grams. Let me write that again. 18.48 grams. Okay, so this is the mass that you should weigh for your magnesium sulfate heptahydrate. Okay, that's easy, right? Next. Okay, the same type of problem. A laboratory technician needs 1 liter of 0.1 molar copper 2 sulfate solution prepared from copper 2 sulfate pentahydrate. Calculate the mass of the per sulfate pentahydrate required. Okay, we were also given the copper sulfate molar mass, but this has no watt. Okay, so let's start again. Let's start with the concentration. 0.100 mole per liter. Okay, now one. Okay, this is mole of the copper sulfate. So this is CuSO4. So 1 mole of CuSO4. How many mole of the hydrate form? It's still 1 mole. Copper sulfate penta. No, this is pentahydrate. Okay, 5H2O. Now let's calculate the molar mass. Molar mass. We're given the molar mass of copper sulfate, which is 1.51.59.61 plus we have 5 water. So water is 18, right? 5 times 18. Remember, 2 times 1 plus 16. This is from H. This is from O. 2 because there are two hydrogen. Okay, next. So we have grams. Now we still have liters here, and the final volume is 1 liter. So this is just 1 liter. Okay, so this is easy. 0.159 159.61 plus 5 times 18. Okay, we have 24.96 molar grams. Okay, next. Saline, a saline NaCl solution is labeled 0.90% M over V. Calculate the molarity of the NaCl solution. Okay, this is the same thing. We are using still M over V. Okay, remember, if it is M over V, just say per 100 ml. So X grams per 100 ml. Since this one is 0.90%, let's say X is 0.90. So we can say 0.90 grams per 100 ml. That is the same thing as saying 0.90% M over V. Okay, so we want to calculate its molarity. So 0.90 grams. We were given the molar mass, so we can get the mole. 58.44 grams per 1 mole. So grams can be cancelled. Now we want to convert this to liters. Okay, so 1,000, oops, 1,000 ml is equal to 1 liter. We can cancel that. Okay, now 0.9 over 100 times 1 over 58.44 times 1,000. So that would be 0.154 molar. Okay, next. Groundwater sample contains 18 ppm of magnesium ions. Assume the density of water is 1 gram per ml. Calculate the molarity of Mg2 plus in the solution. So now we are again using this ppm. Okay, remember ppm, ppb, ppt, right? This is 10 to the negative 6, 10 to the negative 9, 10 to the negative 12. And we know in M over V units, ppm can be expressed as milligram per liter. This one is microgram per liter. then nanogram per liter. So let's just focus here, milligram per liter, since we are converting ppm to molarity. Okay, so let's say in problem it says 18 ppm. So that's the same saying 18 milligram per liter. Okay, so we want to convert milligram per liter to mole per liter. So only this, we only change this. Okay, 18 milligram. Let's convert this first to grams. 1000 milligram is 1 gram times. Okay, so now we have gram. We can use the molar mass of the magnesium ion. So 24.305 gram, 1 mole of Mg2 plus. Okay, now we can cancel this, cancel this, cancel this, cancel this. Now we got moles per liter, molarity. So 18 times 1 over 1000 times 1 over 24.305. This is very small. 7 point, sorry, 41 times 10 to the negative 4 molar. Okay. See, this is more eye friendly than this. Okay, next. Okay, still ppm. A river water analysis reports 42 ppm of sodium ions. Assuming that the density of water is 1 gram per ml, determine the molarity of sodium ion in the sample. Molar mass of sodium is given here. So as usual, right, 42 ppm. Um, that is the same thing as saying 42 milligram per liter. Okay, this is 42 milligrams, so let's convert it to gram, and then you use the molar mass now since we have the gram. Okay, now we're good to go. So this one can cancel and we are left with mole per liter. So 42 times 1 over 1000 times 1 over 22.99. That is 1.83 times 10 to the negative 3 molar. Okay, pretty small value. Okay, next. I think this was the last one. Okay, this is the hard problem. Okay, remember that the problem we have from the previous video, we used two stock solutions to create a, specific concentrate concentration of a solution. Okay, we have, so in this case we're using nitric acid HNO3. Okay, we have stock A. Let's say this is stock A, 1.80 molar, and we have stock B, which is 0.300 molar, and we want to create this solution. Okay, 0.900 molar, and it should be 500 ml. Okay, from this, by adding both of this, we want to create this. Okay, since they are the same chemical, this is adding this, no chemical reaction happens. Okay, we're just creating a new concentration. Okay, let's solve this. So let's start with the volume. So we know that the final volume should be 500 ml. So we can say that the volume from stock A plus the volume from stock B must be equal to 500 ml. Or in liters, we can express it in 0.500 liters. Okay, so from this, we can say that VB, by transposing this to the other side, okay, VB is equal to 500, sorry, let's just use liters, 0.500 liters minus VA, okay, we got this one. So now we got the volume of VB. Now let's relate this to the molarity, not molarity, sorry, but moles. Mhm. Okay, we were given the molarity of the final solution. So it is 0.900 molar. So we have 500 ml. So this would be 0.500 liters. So remember, this is mole per liters. So when you multiply this, we can get a mole unit. So 0.900 times 0.500 is equal to 0.450 mole. Okay, now we can do this uh, by this is the final mole of the solution. Okay, so by assuming this, we can say that 1.80 molar, which is the concentration of stock A times VA, we can say that we can calculate the mole here. So if you add this with stock B, VB, this should be equal to the final mole, right? From this, we can use this value that VB is equals to 0.500 liter minus VA. So 1.80 molar VA plus 0.300 molar times we have 0.500 liters minus VA is equals to 0.450 mole. Now we can multiply it. Okay, so 1.80 molar, this would be 1.80 molar VA. Okay, we multiplied it. Now this one is 0.300 times 0.300 times 0.500. Okay, that is 0.150. So this is molar. So molar times liter, that would be mole. Then we have 0.300 times negative VA, that would be negative 0.300 molar VA equal to 0.450 mole. Now let's put the same term in um, the same side. Okay. Mhm. 1.80 molar VA plus 0.300. No, this is not plus. Okay. And then this is minus. Okay. Here. VA is equal to 0.450 mole. And this one is placed here since they have the same unit. Okay. Minus 0.150 mole. Okay, let's solve it. 1.80 MVA minus 0.300, that is 1.50 or 1.500 MVA. Now 0.450 minus 0.150, that is 0.300 mole. So if we divide it by 1.50 MVA, sorry, no VA here. Just 0. Just 1.50. Okay, 1.50 molar. Okay, now molar, you know that this is mole per liter. So this one, cancel, cancel. We're left VA in the other side. 0.300 divide 1.50 is equal to 0.2. 0.200 liters. So this one cancel and this one will go up. Okay, this one is 0.200 liters. So that is VA. So now we know VA is 0.200 liter or 200 ml. So simply we can know VB since we know that the final solution is 500. So minus the added VA, we have the VB should be 300 ml. So these are the answer. So this is the volume required from stock A and B, 200 ml and 300 ml. Okay, that's it guys. Thanks for watching and keep practicing.